Welcome to Explained,
Oh,
where we sort of unravel the mysteries of complex topics,
right.
making them, surprisingly clear and engaging.
Yeah.
Today we're diving into the hidden world of internet communication.
Okay.
The silent language that allows our devices to talk to websites, send emails, stream our favorite videos.
Right.
Ever wonder how that actually
I-
works?
It's a fascinating journey into the heart of the digital world.
Yeah,
We'll
yeah.
be exploring the layers of protocols and architectures that make this communication possible.
Okay.
Um,
Before we get started, let's play a little game.
okay.
Can you guess how many different applications are using your internet connection right now?
Oh.
Leave your estimates in the comments. I'm genuinely curious to see your guesses. Now, to
Yeah.
truly understand internet communication, we need to start with the application layer.
Right.
I know it sounds a bit technical,
Yeah.
but it's actually quite simple.
Yeah. Think of the internet as a bustling city with different districts for email, web browsing, video streaming, and so on.
Yeah.
The application layer is like the common language everyone uses to communicate,
Right.
regardless of what district they're in.
So even if I'm browsing online while you're video chatting with someone, we're essentially speaking the same language.
Exactly. It's what allows different applications on our devices to understand each other.
Okay.
Now, within this application layer, there are different ways applications can communicate.
Yeah.
The most common model is the client-server architecture.
Okay. Let's unpack that.
Okay.
What exactly is client-server?
Imagine you walk into a restaurant and order food.
Okay.
You're the client, and the restaurant is the server.
Right.
You make a request, and the server fulfills it by providing your meal.
So when I type in a website address, my browser is the client requesting a web page from the server where the website is hosted.
Precisely. The server then sends back the requested web page to your browser,
Right.
fulfilling your request.
Makes sense. Now, is there any other model apart from this client-server setup?
Yes, there's also the peer-to-peer or P2P architecture.
Okay.
Unlike the client-server model where there's a designated server.
Right.
In P2P, computers connect directly with each other, forming a network of equals.
So it's more like a group of friends sharing files directly with each other rather than going through a central library.
A perfect analogy.
Yeah.
Think of file-sharing networks like BitTorrent, where users share files directly between their devices.
Right.
Each computer acts as both a client and a server,
Right.
sharing resources directly with others. Of course, there are also hybrid models
Yeah.
that combine both architectures like Skype,
Right.
which uses a central server for initiating calls, but then establishes a direct connection for the actual voice or video communication.
That's a clever combination.
Right.
So we've got our different communication models.
Okay.
But what are the essential ingredients for any application to actually send and receive information across the internet?
There are three key elements addressing connectivity and speaking the same language.
Okay, let's start with addressing how do applications find each other in the vastness of the internet?
Think of it like sending a letter.
Right.
You need the correct address to ensure it reaches the right recipient.
Yeah.
On the internet, devices are identified by unique numerical identifiers called IP addresses.
So every device connected to the internet has its own unique IP address.
Exactly. And to be even more precise, applications use port numbers
Okay.
on top of IP addresses to differentiate between various services running on a single device.
Right.
It's like having multiple apartments within a building,
Yeah.
each with its own specific number.
So the IP address gets you to the right building, and the port number directs you to the specific apartment.
Indeed, for instance, your web browser typically connects to a web server on port 80,
Okay.
while email might use different ports for sending and receiving messages.
Right.
This ensures that data is delivered to the correct application on the device.
Got it. So that's addressing. What about connectivity?
Okay.
How do applications ensure that the data they send actually arrives at its destination reliably?
That's where transport layer protocols come into play.
Okay.
You can think of them as the delivery services of the internet.
Okay.
The two most common ones are TCP and UDP, each with its own strengths and weaknesses.
Okay, let's dive into those. What's the difference between TCP and UDP?
Imagine you're sending a package.
Okay.
TCP, or Transmission Control Protocol, is like sending it through a reliable courier service
Okay.
with tracking and insurance.
Okay.
It guarantees that all the data arrives in the correct order
Gotcha.
and even retransmits any lost packets.
Okay.
It might be a bit slower, but you have peace of mind knowing the package will arrive intact.
So TCP is like the meticulous courier ensuring everything arrives in perfect condition.
Yeah.
What about UDP?
UDP, or User Datagram Protocol, is like sending a postcard.
Oh.
It's fast and efficient, but there's no guarantee it will arrive or that it will arrive in the right order.
Right.
It's best for applications where speed is paramount and some data loss can be tolerated,
Okay.
like live video streaming or online gaming.
That's a great way to remember the difference.
Right.
So how do applications decide which one to use, TCP or UDP?
It depends on the application's priorities.
Okay.
If data integrity is crucial, like when downloading a file or sending an email,
Right.
TCP is the preferred choice.
Oh, yeah.
But for applications where speed is more important than guaranteed delivery, like streaming a live video,
Yeah.
UDP is often the better option.
Makes perfect sense.
Right.
We've covered addressing and connectivity.
Right.
Now, what about that third element, speaking the same language?
Just like humans need to speak the same language to understand each other,
Right.
applications rely on specific application layer protocols to structure their messages and exchange information effectively.
So it's like choosing the right dictionary and grammar book to ensure both parties understand each other.
Exactly. For example, the web uses HTTP email, uses SMTP for sending, and POP3 or IMP for receiving, and so on.
Each protocol has its own set of rules and syntax,
Great.
defining how information is exchanged.
It's fascinating how many layers and complexities are involved in something we take for granted every day.
Right.
Before we move on to specific protocols like HTTP, can you tell us a bit about sockets?
Okay.
I've heard that term thrown around in relation to network programming.
Sockets are essentially the doors that applications use to connect to the network.
Okay.
Think of them like the physical ports on your computer where you plug in cables to access the internet.
Gotcha.
Programmers use sockets to build network applications,
Okay.
allowing them to send and receive data over the network.
So it's the interface point between the application and the network, like a dedicated doorway for communication.
Precisely. Now, you might be wondering about security.
Yeah.
We've talked about how applications communicate.
Right.
But what about protecting that communication from prying eyes? After all, we share a lot of sensitive information online. Remember to follow Explained for more fascinating deep dives just like this. That's a crucial question, especially with all the data breaches we hear about.
Right.
How do we ensure our data is safe and secure as it travels across the internet?
Security is paramount in the digital world. One of the most important mechanisms is encryption,
Right.
which scrambles data into an unreadable format,
Okay.
making it incomprehensible to anyone without the proper decryption key.
So it's like putting a message in a locked box that only the intended recipient has the key to open.
Exactly. There are different types of encryption, but one that's commonly used to secure web browsing is called TLS, or Transport Layer Security.
Okay.
It creates a secure encrypted tunnel between your browser and the website you're visiting.
So TLS is like adding an extra layer of protection, like putting that locked box inside an armored truck for added security.
That's a great analogy when you see HTTPS at the beginning of a website address. That S stands for secure,
Right.
indicating that the site is using TLS to encrypt the communication.
So HTTPS means safe browsing. Got it. But how does TLS actually work? It sounds quite complex.
It does involve some cryptographic magic,
Yeah.
but the basic idea is that your browser and the website's server exchange digital certificates to verify each other's identities and establish shared encryption keys.
Right.
This ensures that only the intended parties can access the data being exchanged.
Okay, I think I get the gist of it. It's reassuring to know that these security measures are in place to protect our information.
Right.
We'll definitely have to dive deeper into the world of TLS and encryption in a future episode.
Yeah.
Now, are we ready to explore a specific application layer protocol?
Absolutely. Let's jump into the heart of the web and explore HTTP, the protocol that makes web browsing possible.
Perfect. I'm eager to learn more about how this web-powering protocol works.
Okay. Welcome back to Explained. We're continuing our exploration of internet communication.
Right.
Having already uncovered the basics of the application layer, those essential ingredients like addressing and protocols.
Right.
Now let's delve into the fascinating world of HTTP,
Yeah.
the protocol that powers the web.
Yes. HTTP is something we use every day without even realizing it.
Right.
Every time we load a web page, download a file, or stream a video,
Right.
HTTP is working behind the scenes.
You got it. HTTP stands for Hypertext Transfer Protocol,
Right.
and it's the language that allows our browsers to communicate with web servers,
Okay.
fetching all those web pages, images, and videos we love.
So my browser sends a request to a server, And the server sends back a response with the requested content. It's like a digital conversation.
Precisely. And just like any conversation, HTTP messages have a specific structure.
Okay.
They consist of requests sent from the browser to the server,
Right.
and responses sent from the server back to the browser.
Okay, let's break down these messages. What information do they contain?
An HTTP request starts with a request line,
Okay.
which specifies the method being used,
Okay.
the URL being requested,
Okay.
and the HTTP
Like you
version.
said, what did that mean?
The method indicates what action the client wants to perform.
Okay.
For example, GET is used for retrieving data, like fetching a web page.
Right.
POST is used for sending data to the server, like submitting a form.
Okay.
And head is a bit like asking for a sneak peek, requesting only the headers of a resource without the actual content.
So it's like choosing the right verb to describe the action you want to perform.
Exactly. Following the request line are headers, which provide additional information about the request.
Like what kind of information?
They might include the type of browser being used, the languages the client prefers, and even those little digital breadcrumbs we talked about earlier, cookies.
Right, cookies. Those little files that websites use to remember our preferences.
Precisely. Now, on the server side, an HTTP response starts with a status line, which includes the HTTP version, a status code, and a reason phrase.
Status code, is that like those 404 not found messages we sometimes see?
You got it. The status code provides a quick way for the browser to understand the outcome of the request. 200 means everything's okay. 404 means the requested resource wasn't found, and there are a whole bunch of other codes for different situations.
It's like a secret code between the server and the browser.
Exactly. Following the status line are headers similar to those in the request, providing additional information about the response. And finally, the response might contain the actual content being requested,
Right.
like the HTML of a web page, an image file, or a video stream.
So it's all very structured, with each part of the message playing a specific role.
Exactly. And over the years, HTTP has evolved to become more efficient and powerful.
Yeah.
You might have heard of different versions of HTTP, like HTTP 1.1 and HTTP 2.2.
Yes, I've seen those mentioned. What's the difference between them?
HTTP has gone through some major upgrades, just like software on our phones or computers. HTTP 1.1 introduced features like persistent connections,
Okay.
which allow multiple requests and responses to be sent over a single TCP connection.
Right.
This reduces the overhead of setting up a new connection for every request.
So it's like having a dedicated phone line instead of having to redial every time you want to talk to someone.
A perfect analogy. Now, HTTP 2 took things even further, introducing features like multiplexing and header compression, which significantly boosted performance.
Multiplexing, what's that?
Imagine you're at a buffet and you want to try multiple dishes.
Right.
With HTTP 1.1, you'd have to wait in line for each dish separately. But with HTTP 2, you can grab all the dishes you want at once and bring them back to your table.
So instead of waiting for each request to be completed sequentially, HTTP 2 allows multiple requests to be processed concurrently.
Exactly. This means websites can now load multiple elements, like images, style sheets, and scripts, simultaneously, making browsing much faster.
That's a huge improvement.
Yeah.
It sounds like HTTP 2 really revolutionized the way websites load.
It did, and header compression further reduces the amount of data being transmitted, leading to even faster page loads.
It's all about efficiency and speed.
Precisely, and to pique your curiosity, there's even a newer version, HTTP 3, which uses a completely different transport protocol called QUIC.
Wow.
That offers even more advanced features.
HTTP 3, we'll have to save that for another episode. But before we move on, I remember reading about something called pipelining in the context of HTTP 1.1.
Oh, yeah.
Can you explain what that is?
You're right. Pipelining is a technique that allows the client, like a web browser, to send multiple requests to the server without waiting for the responses to the previous requests. It's like sending a whole bunch of letters at once instead of waiting for each reply before sending the next one.
So it makes the communication more efficient by eliminating those waiting times.
Exactly. But even with pipelining, HTTP 1.1 still faced a limitation known as head-of-line blocking.
Head-of-line blocking. That sounds like a traffic jam in the digital world.
That's a great way to put it. Imagine you're stuck in a line of cars.
Okay.
And the car at the front is moving very slowly. Even though you're ready to go, you can't move forward until the car in front of you does.
Okay, I can see where this is going. So if one request is slow, it holds up all the subsequent requests.
Right.
Even if they're ready to be processed.
Precisely, this could significantly slow down page load times, especially for websites with lots of resources.
So how did HTTP 2 address this problem?
HTTP 2 introduced a feature called multiplexing, which we touched upon earlier. It allows multiple requests and responses to be sent concurrently over a single connection.
Right.
So a slow request no longer blocks other requests from being processed.
Ah, so it's like having multiple lanes of traffic instead of a single lane. Even if one lane is slow, the other lanes can keep moving.
That's a great analogy.
Yeah.
This makes page loading much faster and smoother as resources can arrive and be processed as they become available.
Okay, so pipelining in HTTP one-on-one was a step toward solving head-of-line blocking.
Right.
But HTTP 2 took it a step further with multiplexing. What a journey of innovation.
Yeah.
Now, I know we've been focusing a lot on HTTP, but there's another crucial system that plays a vital role in our online experience.
Right.
Domain name system, or DNS.
You're absolutely right. DNS is another cornerstone of the internet, and it's responsible for translating those human-readable website names like Google.com into those numerical IP addresses that computers understand.
Ah, so DNS is like the internet's phone book.
Precisely. It's what makes it possible for us to type in easy-to-remember names instead of having to memorize those long strings of numbers. Imagine trying to remember the IP addresses for all the websites you visit. It would be a nightmare.
That would be impossible.
Yeah.
Okay, so how does DNS actually work? What happens when I type a website address into my browser?
Behind the scenes, your browser sends a DNS request to a DNS resolver, which is usually provided by your internet service provider.
So the resolver is like a directory assistance service that helps me find the right information.
Exactly. The resolver checks its cache to see if it already knows the IP address for the domain name you requested.
Cache like a local copy of recently accessed information.
You got it. If the resolver has the IP address in its cache, it returns it to your browser and you're good to go.
So it's like checking your contact list on your phone to see if you already have the number you need.
Precisely, but what if the resolver doesn't have the IP address in its cache?
Then it has to look it up somewhere else.
Exactly. The resolver then embarks on a journey through a hierarchical structure of DNS servers,
Okay.
starting with one of the root server.
Root servers, what are those?
Think of them as the master directories for the entire internet.
Okay.
There are 13 root servers strategically located around the world. They don't actually contain the IP addresses themselves,
Right.
but they point the resolver in the right direction.
So they're like signposts guiding the resolver to the right place to find the information?
Precisely, the root server directs the resolver to the top-level domain server for the domain name you requested.
Okay.
For example, if you're looking for google.com, the root server would point to the .com TLD server.
TLD server, that's for the top-level domain like .com, .net, or .org, right?
Exactly. The TLD server then points the resolver to the authoritative name server for the specific domain.
Right. In this case, google.com.
Right.
This server finally has the IP address you're looking for and returns it to the resolver.
So it's a multi-step process with the resolver following clues from one server to the next until it finds the IP address.
Precisely. And once the resolver has the IP address, it stores it in its cache for future requests, making the process even faster next time.
It's incredible how this whole system works seamlessly behind the scenes, making it possible for us to navigate the internet using simple names instead of those complex numerical addresses.
It's one of the foundational technologies that make the internet user-friendly. But what about those peer-to-peer networks we talked about earlier? They don't have a central server.
Yeah.
So how do they handle addressing and discovery?
That's a great question. I'm curious to know how P2P networks manage to connect and share information without a central authority.
P2P networks are a fascinating example of decentralized systems. Some P2P systems do rely on traditional DNS to bootstrap the initial connections.
Yeah.
For example, they might use a well-known domain name to point to a tracker server that helps peers connect to each other. So they use DNS as a starting point, and then they can communicate directly.
Exactly. Other P2P systems use distributed hash tables, or DHTs,
Okay.
which are essentially decentralized databases that map content to the peers that have it.
DHTs, those sound familiar. I think I've come across that term in the context of blockchain technology.
You're absolutely right. DHTs are used in various decentralized systems, including blockchain networks. They provide a way to store and retrieve data without relying on a central server.
It's amazing how these concepts connect across different areas of technology. Speaking of connections, let's take a quick break and come back to explore another critical aspect of internet communication network security. We're back for the final part of our deep dive into internet communication here on Explained. We've journeyed through the application layer, explored protocols like HTTP and DNS, and even touched upon the world of peer-to-peer networks. Now, let's shift our focus to a topic that's more important than ever in today's digital landscape: network security.
Yeah, it's a vast and complex field, but we can break it down into key principles and techniques that help protect our data and communications online.
Okay, let's start with the basics. What are the fundamental goals of network security?
At its core, network security is about ensuring confidentiality, integrity, and availability,
Okay.
often referred to as the CIA triad.
The CIA triad, that sounds intriguing.
Confidentiality means keeping sensitive information private and protected from unauthorized access.
Okay.
Integrity ensures that data hasn't been tampered with or altered in transit.
Right.
And availability means making sure that systems and services are accessible to authorized users when they need them.
So it's like a three-legged stool. If one leg is weak, the whole system is compromised.
A perfect analogy. Now achieving these security goals involves a multi-layered approach using various techniques and technologies.
Right.
One fundamental concept is encryption, which we briefly touched upon earlier in the context of TLS.
Right. Encryption. It's like scrambling a message so that only someone with the right key can unscramble it.
Precisely, encryption transforms data into an unreadable format, protecting it from unauthorized access. There are two main types of encryption: symmetric encryption and asymmetric encryption.
Okay, what's the difference between those?
In symmetric encryption, the same key is used for both encrypting and decrypting the data.
Yay.
It's like having a single key that locks and unlocks a box.
That seems straightforward. What about asymmetric encryption?
Asymmetric encryption is a bit more complex, but also more versatile. It uses a pair of keys, a public key, and a private key. The public key can be shared with anyone, while the private key must be kept. Secret data encrypted with the public key can only be decrypted with the corresponding private key, and vice versa.
So it's like having a mailbox with two slots. Anyone can drop a letter in the sending slot, but only the owner of the mailbox has the key to open the receiving slot and retrieve the letters.
An excellent analogy. Asymmetric encryption is widely used for secure communication, digital signatures, and even cryptocurrencies.
Speaking of secure communication, can you explain how TLS works to protect our web browsing? We talked about HTTPS websites earlier.
Absolutely. When you visit a website that uses HTTPS, your browser and the server engage in a TLS handshake to establish a secure connection.
A handshake like they're agreeing on the terms of the conversation.
Exactly. This handshake involves verifying the server's identity using digital certificates. Think of them like digital passports, agreeing on encryption algorithms and generating shared encryption keys.
So it's like a secret agreement before the actual conversation starts.
Precisely. Once the handshake is complete, all data transmitted between your browser and the server is encrypted, making it unreadable to any eavesdroppers.
That's reassuring to know. But with all the news about data breaches and cyber attacks, it seems like staying safe online is a constant challenge.
You're right. Cybersecurity is an ongoing arms race. As technology evolves, so do the threats. But there are things we can do to protect ourselves.
Okay, what are some essential cybersecurity tips for everyday users like me?
One of the most important things is to use strong, unique passwords. For each of your online accounts, don't reuse the same password across multiple websites. It's also a good idea to enable two-factor authentication whenever possible, adding an extra layer of security.
So strong passwords and two-factor authentication. What else?
Be wary of phishing attacks, which use deceptive emails and websites to trick people into revealing personal information. Think twice before clicking on links or opening attachments from unknown sources.
Okay, don't click on suspicious links. Got it. What about software updates?
Keeping your software up to date is crucial. Updates often include security patches that fix vulnerabilities that attackers could exploit.
Right, those update notifications can be annoying, but they're there for a reason.
Absolutely. And remember to be mindful of what you share online. Think before posting sensitive personal information or financial details on social media or public websites.
So be cautious, use strong passwords, and keep things updated. It seems like a lot to remember, but it's worth it to protect ourselves online.
Absolutely. Staying safe online is a shared responsibility.
This has been an incredibly insightful deep dive into the world of internet communication. We've covered so much ground, from the foundational protocols to the importance of network security.
Yeah, it's been a great discussion.
Absolutely. Now for our final interactive question of the episode, what online security practices do you find most challenging to maintain? Begin. Share your thoughts in the comments. We'd love to hear from you. And before we wrap up, don't forget to follow Explained. For more deep dives into fascinating topics, we're always exploring new ideas, and we'd love for you to join us on this journey of discovery.
Yeah, we're always looking for new ideas, so if there are any topics you'd like us to explore in future episodes, please let us know in the comments.
Thanks for listening to Explained. Until next time, keep exploring, keep learning, and stay curious.